Okay, so welcome back to the lectures. Today, we're going to continue our discussion on resonance, on vibration, mechanical vibration type of problem. Okay, so we've been talking about mechanical vibrations, right? So we've been talking about mechanical vibrations. Okay, so we've been. Just a moment. Okay, so we've been talking about mechanical vibrations, right? So these vibration problems are corresponding to such typically, okay, so very typically, they correspond to such kind of vertical vibration problems. So you have a certain spring attached to the ceiling, and on the other end of the spring, there is a mass M being attached to the spring. Okay, so but the zero position, okay, so the zero position is already elongated. So that means originally the spring might be of certain length, let's say small l, and then it was elongated by capital L. So that means you have mg equal to k of L at the initial position. Okay, and then we have to be denoting the u. Okay, so the u as the relative. Okay, so relative displacement. Okay, so the u is the relative displacement with respect to equilibrium. Okay, so with respect to the equilibrium position, and then we have this equation mu double dot, right? So mu double dot plus gamma of u dot plus k of u is equal to the external forcing by T, right? So that was the equation we have introduced the last time, where M is the mass. Okay, so that's very important. And gamma is what we call it the damping constant, right? So the damping constant, and the K is the so-called Hooke's constant, right? So the damping constant models the damping force acted on the mass when it is moving with a velocity u, and k, Hooke's constant, is the proportionality constant in the resistance force provided by the spring. Okay, so this Fe of t is what we call it external forcing. Right, so the Fe of t is what we call it the external forcing. So that's kind of the what we have been talking about last lecture. So very important thing is that you must be able to model. Okay, so you must be able to model this spring mass system or mechanical vibration. So sometimes it's called spring mass system. Okay, so spring mass system. So you should be able to model such mechanical vibrations or spring mass system by second order equations, where you must realize that which one is M, which one is gamma, which one is K, and which one is the external forcing. So that's going to be pretty important for your future analysis. Okay, so that's for the future of your course. Okay, so that's kind of the mechanical vibration. And then with the mechanical vibration at hand, we've been talking about special cases. For example, if the system is undamped and it is free, okay, so so-called undamped free vibration, okay, so undamped free vibration, then you will be able, okay, so you will be able to solve, okay, so you will be able to solve this corresponding equation, okay, so if that is the case, so that means we've been talking about undamped, okay, so undamped free vibration. Okay, so if you talk about undamped free vibration situation, so that means gamma is equal to 0. Okay, so and if it is a free vibration, it means the external forcing is just equal to 0. Okay, so the external forcing is just equal to 0. Now in this case, okay, so in this case, you will be able, okay, so you'll be able to write the original equation as mu double dot, right? So plus gamma is 0, so that's the k of u is equal to 0, as I showed in this equation. And by characteristics, right? So we've been trying to say things about characteristic equations. Now, by characteristics, you will be able to solve this equation, and the solution will be u of t is equal to a times, okay, so a times cosinuses of omega 0 of t plus b times the sinuses of omega 0 of t. Okay, so where the omega 0 is equal to the square root of k over m, and a and b are determined. Okay, so they are determined by this relations corresponding to those initial conditions, because you have to prescribe the initial conditions. But then the alternative representation says that you can actually, okay, so you can actually write this solution. Okay, so write this solution as r times cosinuses of omega 0 t minus the delta, where you can determine the delta. So we've been talking about last time, where the r, okay, so the r, the amplitude of the vibration is a square plus b square, and the delta is determined by tangent. Okay, so the tangent of delta is equal to b over a. So that's going to be the solution for the undamped free vibration. And if you draw a picture, okay, so if you draw a picture of the graph of this undamped free vibration, so u in terms of times of function t, then there's going to be an initial phase, because the t, when t is equal to 0, okay, so when t is equal to 0, you should start from r cosinuses of delta. That's the initial solution. So if delta is not like 0, or I mean the cosine delta is not equal to 1, you're not going to reach the full amplitude. You're going to start from here, and then the cosine function maybe will be, so the r is the largest positive amplitude, and minus r is the largest negative amplitude. So they're going to be oscillating like in between positive and negative r. Okay, so that's going to be your motion, right? So that's going to be a motion. So you can see that the motion is periodic. Okay, so but what's the period? Well, the period is determined by 2 pi over the frequency omega 0. Okay, so here we have been encountering this frequency omega 0. Okay, so from this formula. Okay, so from this formula, and by which you can calculate the period of this the oscillation. So basically, the undamped free vibration is going to really give you a periodic oscillation, and you would like to determine the frequency as well as the period of this oscillation, right? So this is going to be very important. Okay, so this is going to be very important, and you can see that the frequency. Okay, so the frequency omega 0 is simply determined by the Hooke's constant as well as the mass. So it is actually determined by this m and k, which are intrinsic, right? So which are intrinsic constants related to the system itself. Okay, so related to the system itself. So that's going to be kind of pretty important. Okay, so pretty important, and that's what we call it the natural frequency. Okay, so the natural frequency. Okay, so the natural frequency. The natural frequency is going to be omega 0 is equal to square root of k over m. So no matter what mechanical vibration problem, okay, so no matter what kind of mechanical vibration problem you're going to encounter, you must be able to calculate the natural frequency. And this is a formula that you have to memorize. Okay, so that's going to be very important. And you see that in order to memorize this formula, you just have to calculate k. You just have to kind of identify k, which is the Hooke's constant for the problem, as well as the m, which is the mass for the problem, and you divide it, you do k over m and take a square root. So that's a formula that you must memorize. If there is a question asking to calculate the natural frequency, then you must be able to know that it is the square root of k over m. Okay, so that's the natural frequency. Okay, so natural frequency, very important. Okay, very important. Now, with the understanding of undamped free vibration, okay, so with the understanding of the undamped free vibration, are we able to calculate? Okay, so are we able to calculate damped free vibration? Okay, so So by free vibration, it always means, okay, so it always means the external force is zero, but there might be some damping. Okay, so let's say damped free vibration. Okay, so let's talk about the damped free vibration. So the damped free vibration means the gamma is greater than zero, the external force is just equal to zero. So that in that case, you're going to have mu double dot plus gamma of u dot, right? So now you have the damping plus k of u is equal to zero, right? So you're going to have something like this. Now, in order to solve this equation, you have to use the characteristics. So that means the characteristic equation, right? So the characteristic equation is going to take the form mr squared plus gamma of r plus k is equal to zero. So that's the characteristic equation. We're going to solve, okay, so we're going to solve for the two roots, r1 and r2 is minus gamma plus minus the square root of gamma squared minus 4km, right? So divided by 2 of m, right? So that's going to be your two roots for the characteristic equation. So in that case, as we have seen earlier, okay, so as we have seen earlier, once you have the characteristic equation, we have to discuss, right? So we have to discuss the different cases about the essence of the characteristic roots, right? So for example, if both the two roots are positive, right? So if both the two characteristic roots are positive, then what is going to happen, right? So then what's going to happen? So what's happened here, okay, so what happened here is that if both characteristic roots are positive, both characteristic roots are real, it means that the discriminant must be positive, right? So the discriminant must be positive. Okay, so if you have a discriminant is positive case, then we have to kind of see, okay, so let's see gamma squared minus 4km, the discriminant is positive. Then you can see that the R12, okay, so R12 is a minus gamma, okay, so, and then it's plus the square root of gamma squared minus 4km divided by 2 times m. Okay, so let's say this is the R1, right? So the R1. Then you're going to also have an R2, right? So you're going to have an R2 is minus gamma minus the square root of gamma squared minus 4km divided by 2m. So apparently R2 is going to be negative, right? So there's no doubt that R2 is going to be a negative number. But what about R1? Well, R1 is still negative, I claim, because the gamma square. So basically, the fact is that gamma square minus 4km must be, okay, so the gamma square minus 4km must be less than gamma square because k is positive. This is Hooke's constant. And m is the mass, so the mass is also a positive number. So that's going to be less than gamma square. If it is less than gamma square, okay, so if it is less than gamma square, you can see that and if it is positive, right, so as you assumed, then the gamma square minus 4km is going to be less than gamma, right? So it's going to be less than gamma, right? So that's going to be your observation, right? So with this observation at hand, you can see that this one is still negative because if you, that means this gamma square minus 4km is minus subtracting gamma. So that actually further implies that square root of gamma square minus 4km minus gamma is going to be less than 0, which means that R1 is less than 0. So both the real roots, okay, so if the discriminant is positive, then you find that both the real roots are going to be negative. Okay, so if both the real roots are negative, you can see that solution u of t is c1 e to the power of r1 of t plus c2 e to the power of r2 of t. And both are negative. So r1, r2 are both negative. So how does the solution look like? Well, the solution is not going to oscillate at all, right? So the solution is not going to oscillate at all, but rather the solution is going to be just an exponential function. So as a function of t, u of t as a function of t is just exponentially decaying. And why is that the case? Well, you can see that here, if gamma square minus 4km is positive, it means gamma square is greater than 4km. So that means a pretty large gamma. And what does the gamma mean? Well, gamma means the damping. So imagine you have a system, right? So imagine you have a system immersed in some kind of material. And if gamma is positive, so it means that there is going to be friction exerted on the mass. And if gamma is very large, it means the friction is huge. So you can imagine that the mass is kind of immersed in oil or something like that. And therefore, the motion, oscillation, is kind of pretty hard. And most of the time, it is being damped. So that means the motion, okay, so starting from the initial position, the u of t, the motion is not going to be kind of any kind of oscillation, but it's going to just damp to the equilibrium. Is that good, February? Okay, so that's kind of the case when gamma is large. And this case, sometimes we call it overdamped. Okay, so in this case, sometimes we call it overdamped. Okay, so that's sometimes we call it overdamped. Is that good, February? Okay, so that's going to be the situation. Now we can discuss other scenarios. For example, when gamma squared minus 4km is negative, right? So you're going to have two complex roots, right? So it's negative. Then the R12, okay, so the R12 is equal to, is going to be equal to lambda plus minus I times mu, right? So lambda plus times I times mu, where lambda can be calculated, right? So lambda can be calculated as minus gamma over 2 times m. And mu, okay, so the mu can be calculated as 4km, okay, so minus gamma squared divided by 2 times m. Here, I have flipped the sign because I want to have a positive number. So there is going to be an imaginary unit being described here. Okay, so that's going to be the scenario. And in that case, the u of t, according to our theory for second order equations, it is going to be c1 e to the power of lambda t of cosinuses of mu t plus c2 e to the power of lambda t sinuses of mu t. Remember, the real part enters the exponential, and complex part is going to enter sine and cosine. As long as you have this, you can see that because lambda is negative, the profile of the u of t, okay, so the profile of the u of t is still going to be decaying exponentially, but there's going to be an oscillation with a period, with a frequency given by mu. So in the end, the picture of the oscillation is going to be something like this, right? So let's say the major profile is going to be exponentially decaying, but your solution is going to be like oscillating, okay? So that means you have two exponentially decaying function, and your solution is just oscillating in between. But as the oscillation goes, as the time goes, the oscillation is going to be smaller and smaller with the amplitude, and in the end, it's going to converge to 0, because the e to the power lambda t is going to be dominant as t is large, but when t is small, you're going to mostly have oscillation. So this is a phenomenon. Sometimes we're going to call it the underdamped case. Okay, so that means sometimes we're going to call this situation underdamped. Okay, so that's going to be underdamped. Okay, so underdamped, right? So that's going to be the underdamped case. Why it is called the underdamped case? Well, it is called the underdamped case because there is not enough damping, right? So there's not enough damping. So so what happened here is that gamma is less than square root of 4km, right? So that's going to be the choice of gamma. So that means the oscillation is corresponding to a relatively small gamma, so that there's not going to be much friction exerted on the system. Remember, if there's no friction, we're going to call it the undamped free vibration. You're just going to have periodic oscillation. So if there is a friction, then you're still going to have periodic oscillations. I mean, if the friction is not large, but still you have a friction. So you're going to have oscillations, but the oscillations is going to be damped as time goes. Is that good, February? Okay, so that's why we call it the undamped free vibration. Of course, one can also consider the critical case. Okay, so that means gamma squared minus 4km is equal to 0. This is what we call the critical damping. Okay, so critical damping situation. Then you're going to have a solution. Okay, so you're going to have a solution u of t. Okay, so as described here is equal to a times e to the power of rt plus b. You have to use the golden principle where t times e to the power of rt, where the r, the common square root, is because this is 0, so that R is reduces to the gamma, is just minus gamma over 2m to the lambda, which we calculated before. So with that R at hand, you can see the solution is still, and there's no oscillation, but the solution is going to be like in the critical case, the solution is going to be not exactly exponentially decaying, but exponentially decaying altered, right? So corrected by t. So that's a e power rt plus b times t times e power of rt. Is that good for everybody? Okay, so that's going to be the scenario. Okay, so that's going to be the scenario. So that kind of means that the critical gamma is 2 square root of k times n. Right? So the critical gamma, which exerts kind of a critical damping, where you're still going to have decay, but the decay is not going to be that fast. So the decay might be something like this. It's not going to be as fast as the exponential. Is that good for everybody? Okay, so there are 3 kind of phases for the damped free vibrations, where you can see that the magnitude of the damping is going to play a critical role here, right? So the harder, basically the situation here is like a competition between oscillation and damping, right? So there's a competition between oscillation and damping. If the damping is very large, then your system is tend to do more exponentially decaying. If the damping is very small, system is more to do oscillation, right? So basically damping is fighting against oscillation, and in between you're going to have a trajectory that does not decay as fast as exponential, but still decays, right? So that's going to be your scenario. Okay, so that's going to be your scenario. Okay, so here is a nice exercise that we would like to practice together. Okay, so the problem says that you have a spring which is hanging vertically from a rigid support. It is stretched 6 inches by a mass that weighs 8 pounds. The mass is in an equilibrium with a damping constant of 0.25 pound-second per feet, and acted on by external downward force 4 cosine 2t pounds, right? So suppose that the mass is displaced additional 2 feet in upward direction, then released. Can you set up but do not solve an initial value problem that models the motion of the body? Okay, so in order to solve such problems, it is sometimes a good idea. Okay, so when you are on an exam, okay, so it is sometimes a good idea to draw a picture. Okay, so this is always what I always recommend to people who are about this practical type problems, right? So what does it say? You have a spring hanging vertically from a rigid support. It is stretched 6 inches by the mass that weighs 8 pounds. So that means you have an original. Let's say you have an original. This is the original length of the spring. Now it is stretched 6 more inches, right? So the stretching, the initial stretching is given by 6 inches, right? So it is stretched by 6 inches by a mass that weighs 8 pounds, right? So by a mass that weighs 8 pounds. So you can draw the mass here. M is equal to 8 pounds, right? So sorry, this is not the mass. It is that the weight, right? So that means you're going to have the mass, but the mass is going to satisfy the fact that mg is equal to 8 pounds, right? So it's equal to the described 8 pounds, right? So that's 8 pounds. So I'm going to ignore the measurement of the units of measurement. Okay, so that's going to be the situation. The mass is in a medium with damping constant. So from here you can see at least you can calculate the mass is equal to the 8 divided by the gravitational constant. G is equal to 32 if it is measured in pounds. So that 8 over 32, you got the mass. So the mass is there, right? So, and then you want to calculate the damping constant, right? So, and here it says that medium is with the damping constant 0.25 in terms of pounds and feet, right? So let's say you can use that constant. So that gamma is 0.25 in terms of pounds and feet. And then you want to know the Hooke's constant, right? So how do you calculate the Hooke's constant? Well, because of the picture, the initial stretch is about 6 inches, so that mg is equal to KL. Well, L is 6 inches, but you have to use a feet, right? So important problem important point for these kind of practical problems is that you have to use a unified system of your measurement. If every length is measured by feet, then you cannot use inches. You have to transfer inches into feet, right? So 6 inches, every inch is 1/12 feet. So I mean 1 feet is 12 inches. So 6/12 is 1/2. As long as you have this, you can see that the Hooke's constant is equal to mg over L, but mg is equal to 8, L is 1/2, so the Hooke's constant is going to be 16. So you get Hooke's constant. And then it says that the mass is external force is downward by 4. So downward, remember, downward direction is positive, right? So we've been talking about it last time, that the downward direction is going to be positive. So that means you have to know, you know the external forcing, right? So the external forcing is 4 times cosine 2t, okay? So 4 times cosine 2t. So with all this at hand, you can just kind of put all these parameters into the equation that is the standard, right? So this is the standard equation that you have to memorize. But for our practical problem, m now is equal to 1/4. So you get 1/4 u double dot plus gamma is equal to 0.25, right? So that's going to be another 1/4 of u dot plus k. K is equal to 16, right? So 16 times u is equal to the external forcing is 4 times cosinuses of 2t. So that's kind of the way how you get the solution to the problem. This is the equation. Remember here, usually, okay, so on the exam, they're going to say set up, but do not solve. You don't have to solve this equation. So do not do extra work. That's not needed because it's going to take your time. You remember your exam is not only consists of problems, but also time restricted, right? So you cannot exceed the given amount of time. Therefore, you have to reduce as much as the unnecessary work, right? So it's not necessary to solve this equation, but you just formulate the problem. But however, the situation is not finished yet because it says that can you set up but do not solve an initial value problem that models the motion of the body. So it has to be an initial value problem. How do you solve this initial value problem? Well, initial value problem means that here it says you have to know the initial position. So you have to know u of 0 and you have to know u prime of 0, initial velocity. Because this is a second order equation, in order to fully recover the constants, unknown constants in this equation, you have to know the initial position and the initial velocity. So how to find the initial position? Well, the initial position means that the mass is displaced additional 2 feet in upward direction, then released. So additional 2 feet, according to our picture, it means that additional 2 feet, it means that it's going to move up a little bit. Remember, this is the equilibrium position where u is equal to 0. So it moves up a little bit, right? So let's say 2 inches, right? So 2 inches, right? So 2 inches, that means, but upward direction is negative, downward is positive. So that means, so this is the actual position of your mass. It just has to be moved up to 2 inches. So that kind of says that u of 0 is -2 in terms of inches, right? So you have to divide by 12 in order to get feet, right? So in order to get feet, right? So 2 feet, sorry, additional 2 feet, right? So it is additional 2 feet, right? So that means you don't have to do the division by 12, right? So it's already 2 feet, right? So sorry for the excuse me for the unnecessary work. So the 2 feet is actually a picture, okay? So I mean, it's not quite necessary to draw this picture, but if you like, you can draw it, right? So the 2 feet is going to be pretty much higher above, okay? So I'm not going to quite do it, okay? So you can kind of move it pretty much above, okay? So, but you remember that this is a -2 because it is moving upwards, and the upward direction is negative, okay? So, and then the release, when you release, it's just freely released, so that u prime of 0 is 0 because you are not going to give it initial velocity. So that's going to be your situation. Okay, so that's going to be your situation. Okay, so that's going to be the problem. Is that good, family? Okay, so that's going to be the situation. So here, for the rest of today's lecture, okay, so for the rest of today's lecture, I like to talk about a pretty interesting and nice phenomenon in classical mechanics that can be explained by ordinary differential equations. So from here, you will see the power of taking the ODE class is that once you take this class, we get the ability, okay, so we get the ability of doing reasonable predictions. Okay, so reasonable predictions from ordinary differential equations. Okay, the study of ODEs give us the ability to do pretty nice and important predictions related to classical mechanics. Okay, so related to classical mechanics. Okay, so that's going to be a scenario which we're going to call it the resonance. Okay, so that's going to be a scenario which we're going to call it the resonance. Okay, so what does resonance say? Okay, so what does resonance say? Well, resonance is such a phenomenon. Okay, so resonance is such a phenomenon. Okay, so where you're going to consider the external forcing to be periodic. Okay, so what happened here is that we're going to consider the situation mu double dot. Okay, so plus k. Okay, so sorry. So plus gamma. Okay, so say for example plus gamma of u dot plus k of u is equal to the external forcing. But the external forcing is going to be an amplitude. F0 is the amplitude of the external forcing, and then the cosine omega of t. Okay, so I'm going to consider a solution of this form, an equation of this form. So the external forcing is going to be periodic. Okay, so you can see that external forcing has an amplitude. So F0 is the amplitude. Is the amplitude of the external forcing, and omega is the frequency. Okay, so omega is the frequency of the external force. And remember here, for the left-hand side of the problem, there's going to be a natural frequency, the square root of k over m, right? So that's going to be called the natural frequency. Okay, so natural frequency. That's going to be a natural frequency of this problem, right? So natural frequency not necessarily equal to the frequency of the external forcing. Okay, so there are, just to remind you, there are two omegas here. There's natural frequency omega 0, which is the frequency of the undamped free vibration, and there's an omega, which is the frequency of the external force. Is that good for everybody? Okay, so now we can actually use characteristics. Okay, so we can use characteristics to solve this equation. Okay, so we can use characteristics to solve this equation. Okay, so let me take my textbook. Okay, so while it is starting up. Okay, so and we can use kind of a method. Okay, so this is probably a real case that we are going to make use. Okay, so they're going to make use of the textbook. Okay, so but it is indeed necessary here. Okay, so it is indeed necessary here. Okay, so let me take a look at okay, so forced vibrations. Okay, so let me take a look at forced vibrations. So what happened here is that this problem, okay, so this problem can actually be solved. Okay, so it's there's a procedure of solving this equation, and I would not kind of repeat it in this lecture, but I would like to just remind you that you can solve it by first considering the so-called complementary equation, right? So this is our standard procedure. Is that you must start from the complementary equation, which means that mr square, muc, okay, so the complementary equation, which simply means that you're going to remove the right-hand side, right? So uc double dot, right? So, okay, so, right? So you want to solve this complementary equation by gamma uc dot plus k of uc is equal to 0. You could work with the complementary equation. As long as you have the complementary equation, it's going to give you the complementary solution. But then you're going to just find a particular solution, right? So a particular solution, let's say u of t, right? So that satisfies this equation. How do we find a particular solution of a non-homogeneous problem if the right-hand side is sine or cosine? Well, you're going to try like a sine of, let's say a cosine. Let me start from cosine. Okay, so a cosinuses of omega t, right? So a cosinuses of omega t plus b times sinuses of omega. This is standard. This is what so-called method of undetermined coefficient. This is a good kind of review of what we have been learning so far. You have to use the method of undetermined coefficient and just determine the coefficients a and b. And as long as you have that, then you're going to have the general solution. Okay, so let's say the general solution is just going to be u of t is equal to the complementary solution plus the particular solution. And that's going to be the procedure of solving this kind of problem. So you can really do that. Okay, so you can really do that. Here you can see they're trying to have a general solution. This is the complementary as well as the particular solution. You find the a's. So I'm not going to quite do that. Okay, so I'm not going to quite do that. But in the end, the solution. Okay, so finally the solution is going to take such a form. Okay, so let me see if I can take a snapshot here. Okay, so so the final solution. Okay, so the final solution is going to take take such a form. Okay, so so let me see if I can paste it here. Okay, so let's. Okay, so we can paste this picture here. Okay, so that's going to be the final solution. It's going to be taking such a form. Okay, so however, the point here is that in this case, okay, so the point here is that in this case, the constants, this constant used here are a little bit different from what we had before. Okay, so we were using gamma as our damping, right? So we were using gamma as our damping. But here, the gamma is, so if you look at the textbook type of problem, okay, so here they're going to use gamma as the omega, okay, so that's basically their gamma corresponding to our omega. So maybe I will cut this one also, okay, so it's a good idea to cut this equation also because it's just a little bit disagrees with what we have been doing so far, okay, so maybe I'll paste it here. Okay, so paste it here. So that's what happens to this equation. Okay, so you can see that their gamma is actually our omega, right? So it is actually our omega, and their b is our gamma. So in the end, you can see that this is the part for uc of t. This is the part for the particular solution, and this maybe we'll write it as u of t. Is that good for everybody? Okay, so that means the u of t, okay, so the u of t has an amplitude, right? So the amplitude, okay, so the amplitude of particular solution, right? So particular solution in terms of our parameters is just going to be f of 0 divided by the square root, okay? So the square root of this kind of number, which is k minus m of omega squared plus gamma square of omega squared, right? So here, remember, b is now gamma and gamma is now omega, right? So that's, we have to stick to this equation. Is that good for everybody? Okay, so as long as you have this, you can see that the amplitude of this particular solution has such a denominator, right? So has such a denominator. Now let us consider the scenario when gamma is very small, okay? So when gamma is very small. If gamma is very small, then if omega is equal to the square root of k over m, then you can see that this simply means that omega squared multiplied by m minus k is 0. So this one will be 0, and this one will be very close to 0. Is that good for everybody? So in that case, the amplitude of the particular solution is going to be super large. Is that good for everybody? Okay, so let's summarize this observation. What does this observation give us? Well, the observation gives us that the amplitude of the particular solution is going to be huge if the omega, where the omega is actually the frequency for the external forcing. If the frequency of the external forcing is equal to K over M square root is the natural frequency. Is that good for everybody? Okay, so basically what I'm saying is that if the omega is chosen as the natural frequency, okay, so if the omega is chosen as the natural frequency, and the gamma, okay, so remember the damping constant is super small, in that case, the amplitude of the particular solution is going to be huge. So this is a phenomenon that we're going to call it resonance. So what does resonance mean? Resonance means that you're giving the mechanical vibration a kind of periodic external forcing with a frequency given by the omega. And what happens here is that if the damping is small, so this resonance must happen under the assumption that the damping is small. If the damping is small, okay, so you have two ingredients for resonance, that the damping must be small, and then if the external forcing has a frequency that's equal to the natural frequency. Natural frequency is the square root of K over M, is the natural frequency of the system, then a resonance is going to happen. And when resonance happens, the amplitude of your oscillation, in particular, this amplitude for the particular solution, which it kind of tells you how much oscillation there is for the oscillating solution, is going to be huge. So you're going to create a huge motion that might destroy the whole system. So this is called resonance. Okay, so you must remember that resonance occurs under two scenarios. One is that the damping is small. The other one is that the external forcing has a frequency that's equal to the natural frequency. Then in that case, you're going to have resonance. Okay, so you're going to have resonance. So this is kind of going to be pretty important. Okay, so this is kind of going to be pretty important, and it is usually tested on the exams. Okay, so they usually tested on the exams. Okay, so we can see that for a slightly damping or no damping system, when omega external forcing has a frequency that's near the natural frequency, the amplitude is large, even for relatively small external forces. Okay, so that's going to be the situation. So let's look at the problem. Okay, so for example, this problem says you have a body weighing 8 pounds hanging from a vertical spring attached to the ceiling. At the equilibrium position, body stretches the spring 1/2 foot from the natural length. The body is started in motion from the equilibrium position with initial velocity 4 feet per second in a downward direction, right? So assume there's no damping and the body active external force, can you set up the problem? And if the given downward external force is replaced another force where you have an omega to be chosen, remember here the omega is to be chosen, and can you find the value frequency omega which is going to cause a resonance, right? So that's going to be a problem with resonances. Okay, so you can easily set up this equation. Okay, so remember, so let's quickly go over it. It weighs, so it's pretty much similar to the previous problem, right? So here the weight is 8 pounds. In terms of mass, you have to divide by g, so you get 1/4. And then the gamma is 0 because there's no damping, right? So there's no damping. Okay, so and what about the k? Well, mg is equal to kl. So the 8 divided by L, so L is 1/2 feet, so you get 16. External forcing is 3, so I'm going to quickly, okay? So external forcing is 3 cosine 2t, so you can easily formulate such a problem. Okay, so with the initial conditions, how do we have the initial condition? Well, here the initial conditions are a little bit strange because the body is starting a motion from the initial position with the initial velocity 4 feet per second and downward direction. So that means the initial position is 0, but the initial velocity is 4. So that's going to be your situation. But however, here the question is asking you, okay, so the question is asking you, can you find a resonance, right? So can you find a resonance for the omega? So omega is not 2 anymore, but the general omega. Can you find out omega that you're going to have resonance? Well, to solve this problem, it means that you have to calculate the natural. Remember here, gamma is actually equal to 0. So there's actually no damping. Remember, the resonance must happen on the small or no damping scenario. Okay, so that's on the small or no damping scenario. So you just calculate k over m, right? So the natural frequency, remember, is k over m, take a square root. Then you have the k, you have the m. So you can calculate the natural frequency to be 8. And this is going to be your omega. Is that good for everybody? Okay, so when you choose this omega, you're going to realize resonance. So that's going to be the kind of a very simple problem where it is about resonance. And this is actually the type of problems you're going to see on your exams. Okay, so this is actually the type of problems that you're going to see on your exams. Okay, so that's going to be the scenario. Okay, so now let's look at one more problem. Okay, so one more problem just to practice. Okay, so here it is using kilograms. So I have 3 more minutes. Okay, so 20 kilogram body hangs from a vertical spring attached to rigid support. At the equilibrium position, body stretches the spring 50 centimeters beyond the natural length. Body is acted on by external force of 10 cosine 2t newtons and moves in a medium with a damping constant 100 newton second per meter. Okay, so can you set up the problem? And second thing is that, are you going to have resonance? So this very similar to what we had before. But here, the kilogram is just the mass, so m is just 20. And gamma is equal to 100. Here we're using Newton. So therefore, we have to use the international standard, like 50 centimeters, which means that the K is the mg. So 20 multiplied by the gravitational constant, in this case is 9.8, divided by the initial stretch, which is like 50 centimeters, is 1/2 meters. So 1/2 meter. So that's the K, and you're going to have external forces, and therefore it is easy to set up the problem with the initial position and initial velocity. What is the initial position? Well, here it says that start motion from equilibrium, initial velocity is upward with 20 centimeters per second. So that means 20 centimeters is 0.2 meters. Is that good for everybody? Okay, so you're going to have minus 0.2. You're going to set up the problem. Now, question is, are you going to have resonance? When are you going to have resonances, right? So, but here you can see that the damping constant is huge, right? So some people ask, what is huge, what is small? Well, 100 is definitely huge. Maybe it's if it is 0.1, you can say it's small. Is that good for everybody? Okay, so 100 newtons is definitely huge. So do not be puzzled by this problem. Indeed, there is no frequency that it is going to cause resonance. Because even if you tuned the omega to be equal to the natural frequency, the gamma is huge, and you're going to be quickly damped. Remember, in our damping situation, you're going to be quickly damped because you have an overdamped situation. There's going to be no resonance, even if you would like to. If you would like to tune the external force to have the frequency as the natural frequency. Is that good for everybody? So remember that the resonance happens under 2 scenarios. The first scenario is that the damping is small. The second scenario is that the frequency, the external frequency, is equal to the natural frequency. Then you're going to have resonance. But if the damping is huge, then there's you do not even have preliminary assumptions, and there's nothing going to talk about frequency, the resonances. Is that good for everybody? Okay, so this lecture, we've been talking kind of about resonances and how the resonances occurs. Most important thing is that you must remember the natural frequency is equal to square root of k over m, and you have to be able to calculate the natural frequency. Okay, so as examples, here I have listed quite a few exercises that you might practice throughout your spare time about this kind of mechanical vibration problems. Okay, so that's what I want to say for today's lecture. Let's come back to the next lecture and we will continue our course. Okay, so much for today's lecture.